Welcome to another lecture in the course on 3G and 4G wireless mobile communication systems. In the last lecture, we started with analyzing the properties of PN sequences. For instance, we had looked elaborately at the generation of a PN sequence using a linear feedback shift register. We had then subsequently looked at several properties of the PN sequences. For instance, here I have the shift property or the cyclic shift property of the PN sequence. Then we had also started considering random spreading sequences where each chip is generated randomly as plus or minus 1 with probability a half, and each chip C I is independent of another chip C j. We said that the expected value of each chip is 0. We also said that if we look at the correlation, that is the self correlation, that is C0 I plus k summation divided by n, that is correlation for a lag of k, that correlation value, expected value of that is 0, and the variance of that self correlation at lag k is 1 over n. For k not equal 0, that is for any lag that is strictly greater than 0, that is k equals 1, 2 and so on, and for any lag that is less than strictly less than 0, that is k equals minus 1, minus 2 and so on. Now, to complete this discussion, let us look at the correlation at lag 0, and that is fairly simple. If I consider the self correlation R 0 0 at lag 0, I will define it as 1 over n summation over I C 0 of I into C 0 I plus k, but k here is 0. So, this is simply C 0 I. In other words, this can be written as 1 over n summation over I C 0 square I. Now, remember each C 0 is I is plus or minus 1 with equal probability. In any case, C 0 square of I is always 1 because C 0 I is plus or minus 1. Hence, this is 1 over n summation of I 1, which is equal to n over n, which is 1. Hence, the self correlation at lag 0 is 1, which is trivial because it's you are correlating the sequence with itself. Now, let me summarize the properties of the correlation of the self correlation or the auto correlation. R 0 0 of k, as we have seen, is equal to 1 if k equals 0, and its expected value, this is a random variable, remember. So, its expected value of R 0 0 k equals 0 with variance 1 over n if k not equals 0. That is, if k equals 0, then it is a deterministic quantity. R 0 0 k is 1, that is R 0 0 is R 0 0 of 0 corresponding to lag 0 is 1. If k is not 0, then R 0 0 k is a random variable with expected value 0 and variance 1 over n or power 1 over n, as we saw earlier. Expected R 0 0 square of k equals 1 over n, that is its variance is 1 over n. Now, let us look at the cross correlation properties of two random spreading sequences. So, let us look at the cross correlation properties of these PN sequences or these random sequences. If I look at the cross correlation, for that purpose, let me consider two code sequences COI and C1 I, such that 1 less than equal to I less than equal to n and 1 less than equal to I less than equal to n. By cross correlation, I mean the correlation between the code sequence 0 and 1 corresponding to a lag k. So, similar to R 0 0, let me define R 0 1, the correlation between sequence 0 corresponding to user 0 and the correlation between sequence 1 corresponding to user 1 as R 0 1 of k equals 1 over n summation over I C O of I into C 1 of I plus k. Now, if I take the expected value of this cross correlation for lag k, if I look at the expected value, that is expected value of R 0 1 of k, that is equal to 1 over n summation over I. I am going to take the expectation directly inside, since we have done this a couple of times, because the summation and expectation are both linear operators, hence we can interchange them. So, this becomes expected C 0 I expected C 1 I plus k, and there is a summation over I, and you divide over 1 over. Now, this, as we have seen yesterday, that the code sequences corresponding to user 0 and user 1 are independent, because not the chips are generated independently. Hence, this expectation of C 0 I into C 1 I plus k is nothing but the product of the expectations expected C 0 I expected C 1 I plus k, which is equal to 1 over n summation over I. Expected C 0 I is 0, expected C 1 I is 0, hence this is 0 0. Hence, the expected cross correlation 0 1 k for any lag. Now, observe that this is true not only for any non-zero lag, but this is also true for k equals 0, because even when k equals 0, unlike in the cross correlation, C 0 I into C 1 I are both independent, hence this again splits into expected C 0 I expected C 1 I, which is 0. Hence, the cross correlation is much simpler for any lag k, 0 or non-zero, the cross expected value of the cross correlation is always 0. And going by the similar analysis as we did for the autocorrelation, one can easily prove that the expected value of R 0 1 square of k equals 1 over n. This is not very difficult. Let me highlight the salient steps of this derivation. R 0 1 of k equals 1 over n summation I C 0 of I into C 1 of I plus k. Now, the product R 0 1 square of k is R 0 1 k times R 0 1 k, which is 1 over n square summation I summation j C 0 I C 1 I plus k C 0 j C 1 j plus k. I will take the expectation on both sides, and now I will move the expectation operator inside, and that is easy to see that this reduces to summation over I summation over j expected C 0 I C 1 I plus k C 0 j C 1 j plus k. Now, we can clearly see if I is not equal to j, then all these split into independent terms. This is expected C 0 I into C 1 expected C 1 I plus k into expected C 0 j into expected C 1 j plus k, because the chips corresponding to different code sequences, and the different chips corresponding to the same sequence are also independent, hence this splits into 4 different expectations, except when I equals j. In that case, this reduces to summation over I expected C 0 square I into expected C 1 square I plus k, and we know each C 0 I and each C 1 I plus k is either plus or minus 1. Hence, each of these quantities C 0 square I, C 1 square I plus k are both 1, hence this product is 1. Hence, this reduces to expected R O 1 square k equal 1 over n square summation over I of 1, which is n over n square, which is equal to 1 over n. Hence, if I look at the cross correlation at lag A, the relationship is much simple. If I look at cross correlation at lag A, R 0 1 k, that is the cross correlation at lag k, expected R 0 1 k is 0, and the power or the variance, that is expected R 0 1 square of k equals 1 over n. So, the cross correlation has a much simpler relation. If I look at the cross correlation at lag k, the expected value is 0 and the power of the variance in that is 1 over n. So, if you look at it, if you look at these code sequences, these long code sequences used by different users, they have a very where each chip can be assumed as randomly generated with randomly generated as plus or minus 1 with probability half for plus 1 as and half for minus 1, you can see that each of these behaves as a random sequence such that the correlation, expected value of the correlation is 0 and variance in the correlation, variance of the correlation is 1 over n, except for the autocorrelation when the lag is 0, then the correlation becomes, that is, if you self correlate a sequence at lag 0, then the expected value is deterministic. In fact, it is always 1. So, except for that single case, the correlation and the cross correlation are always, expected value is always 0 and random, and the power or the variance of this correlation is 1 over n, and that plays a big role in distinguishing these information symbols that are transmitted corresponding to the different users on in a CDMA system, because these codes, remember, are orthogonal, except, I mean, remember we started with orthogonal CDMA codes, except now we have moved from deterministic codes to random codes, and we are still saying that in the expected sense the correlation between these codes is 0. I mean, earlier we said the deterministic correlation, that is A0 transpose or C0 transpose C1 was 0. Now, we are saying that does not hold in a deterministic sense, but yet in an expected sense, that is, if I look at the expected value of code 0 dot product with code 1, that is still 0, but if I look at the power, there is still a small power in the cross correlation, which is the variance, which is 1 over n, and that slowly tends to 0 as n tends to, as the sequence n becomes, as the length n becomes larger and larger, that variance tends to 0. Alright. So, this plays an important role in multi-user CDMA, which is the topic we are going to come to next. Now, how do these random codes help in code division for multiple access? That is, how do these random codes that we have seen so far help in multiple access of the different users on in a CDMA wireless communication systems? How can I multiplex the different information signals corresponding to user 0 and 1 given these random codes C0 and C1? Let us look at that. So, let us start with the main topic of this section, which is multi-user CDMA. If I go into multi-user CDMA, first let me assume, again as we did before, symbol corresponding to user 0 is A0. Similarly, symbol information symbol corresponding to user 1 is A1. So, let me write that here, symbol to user 1 is A1, that is A0 is the symbol corresponding to user 0, A1 is the symbol corresponding to user 1. Now, I will multiply A0 by the code sequence corresponding to user 0, and I will multiply A1 with the code sequence corresponding to user 1, and I will transmit them simultaneously on in the CDMA wireless system. So, let us see what happens when we transmit them. Each chip yn, which is the transmitted signal, or let me in fact call this xn, because this is the transmitted signal, this is xn, is generated as A0 C0 n plus A1 C1 n. That is the nth chip of the transmitted CDMA signal. Remember, this is the transmitted CDMA signal, which is generated as symbol 0 times chip belonging to C0n, that is code of user 0, plus A1, which is symbol corresponding to user 1, times the chip C1n corresponding to the code of user 1. Now, at the receiver, what happens is simple. I receive this. So, remember, this is a multiplexed signal. Why is this a multiplexed signal? This is a multiplexed signal. Why is this a multiplex signal? Because look at this, this signal contains information symbols A0 and A1, that is, it contains the symbol corresponding to both user 0 and user 1 at the same time. Hence, it is a multiplex signal, only that the symbols are multiplexed using different codes C0n and C1n. At the receiver, you receive this signal, I mean this signal is received in the presence of noise. So, at the receiver, we will have exactly x of n, except there will be an addition of the noise. So, I will receive A0n C0n plus A1 C1n plus W of n, and this W of n is nothing but the noise, and this is additive white Gaussian noise. All right. So, now what am so this is the received signal. So, this is the, let me write this down again clearly, this is nothing but the received. Now, at the receiver, what I will do is I will correlate, similar to what we did earlier, I will correlate this signal with the code corresponding to user 0 to extract the signal corresponding to user 0. So, at the receiver, let me correlate with 0. So, let me define R 0 as the correlation 1 over n summation y of n with C0 of n summation over n. That is, I am taking y of n, correlating it with C0 of n, which is the code sequence. Remember, this is the code sequence corresponding to user 0. So, I take 1 over n, y of n, c of n, summation over n, this is the correlating with the code sequence corresponding to user 0. Now, let us substitute this expression for y of n and see what happens when we expand this thing, expand this received signal, that is we get 3 terms. Remember, y of n has the signal A0 corresponding to user 0, corresponding to user 1, and it also has the noise component. So, we will have 3 components here. The first one is yn, the first one is summation over n A0 C 0 of n times C0 of n. This is the term corresponding to user 0. Then we will have the term corresponding to user 1, which is summation 1 over n A1 C1 of n C0 of n plus 1 over n summation over n, that is the noise. We have the noise term, which is W n C0 of n. This is the corresponding noise term. Now, let me define some nomenclature at this point. We have A0, which is the desired user whose signal we want to extract, that is why we are correlating with C0 of n. Hence, let me call this as, let me call A0, this is the desired user or the desired component. We are trying to decode the symbol transmitted by user 0, hence this is the desired user. This user 1, which is not really necessary, but who is interfering with the desired user in the detection, is known as the interfering user or the interferer, and this interference in CDMA has a name, has a very specific name. This is known as multi-user interference. This is known as multi-user interference and it is abbreviated as MUI. M stands for multi, U stands for user, I stands for interference, hence this is multi-user interference. This is a characteristic of CDMA, because you are simultaneously multiplexing the source, the signals, information signals of different users. They are going to interfere at the decoding process of any user, and that interference is known as multi-user interference, and this is nothing but the noise component. Now, let me write down analyze each term separately. Let me look at the desired user signal, desired user. For the desired user, the desired user component, that is straightforward, that is 1 over n summation over n A0 C0 of n times C0 of n. This is nothing but if I extract A0 out times 1 over n times summation over n C0 square of n, and we know that C0 of n is either plus or minus 1. So, in both cases C0 square of n is 1, hence this is A0 into 1 over n into summation 1, which is A0 into n over n, this is A0. So, the result of the correlation of the desired user correlation with C0 of n yields nothing but A0, which is the symbol of user 0, and that is not surprising, because what is this? This is correlation C0 n with C0 n, that is the auto correlation for a lag of 0, and we said this is the deterministic quantity 1. Hence, once you despread or decorrelate with C0 of n, you get back the symbol A0 corresponding to user 0. So, this is the symbol 0. So, the result of decoding using a random spreading sequence, you see 0 of n yields A0, which is a symbol corresponding to user 0. However, now there is also a multi-user interference component. Look at this, we also have a multi-user interference component, which is A1 C1 n C0 n. So, let us look at how to simplify this component. Let us look at the multi-user interference component, that is the multi-user interference let us look at the multi-user interference component. This is given as follows. Let me call this as I1, this is interference from user 1, this is interference from user 1. So, I1 is the interference from user 1. This is defined as 1 over n summation over n A1 times C1 of n times C0 of n. that is equal to 1 over, that is equal to, let me write this in a form that we are familiar with. This is A1 1 over n summation n C1 n C0 of n. Look at this, this is nothing but the cross correlation for a lag of 0, hence this is A1 times R 0 1. So, hence we can simplify this as follows: the interference or the multi-user interference I1 is nothing but A1 times the cross correlation for a lag of 0. Hence, expected I1 is A1 times expected R01 of 0, which is equal to 0. That is what we have seen earlier, and in fact the power in this interfering component, that is expected I1 square, which is the power in this interference component, or the power in this noise, which is the interference noise, because remember it is a destructive influence on the, or a disruptive influence on the signal that we want to detect at the receiver. The power is nothing but expected A1 square into expected R01 square of 0. Now, expected A1 square is nothing but the power of user 0, because expected A1 square, A1 is the information symbol transmitted by user 1, hence expected A1 square is the power of user 1 into expected R01 square, that is the power in the cross correlation for lag of 0. We have seen this earlier, this is nothing but 1 over n, hence this is P1 time P1 over n. Hence, the multi-user interference component is a random variable with expected value 0, it acts as noise with expected value 0 and power P1 over n. Look at this, if the user P1 transmits a power, the whole of the power is not acting as interference. The power P1 is suppressed by a factor of n, which is nothing but the spreading length, or also known as the spreading gain. Hence, a fraction of the power that is transmitted by user 1 is acting as interference at user 0, and that fraction is P1 over n, and as n tends to infinity, that is as the code length n becomes larger and larger, this interference tends to 0. So, let me also note that additional point, MUI, the multi-user interference P1 n tends to 0 as n tends to infinity. So, if you look at long spreading course, as n increases, the MUI multi-user interference component progressively decreases towards 0. As the multi-user, as the spreading length n increases, the multi-user interference component progressively tends towards 0. Now, there is the third component, which is the noise component, and let us look at what happens to the noise component. So, there is the third component, which is the noise component. What happens to the noise? Let us look at the noise component. Let me call it as W, which is equal to 1 over n summation over n W n times C0 of n. Now, the expected, now given that this is noise, remember this arises, Wn is noise. So, W is nothing but the noise component at the output of the decorrelator. Remember, we are decorrelating with the spreading sequence C0. So, this is the noise at the output of the decorrelator. We are interested in the power and expected value of this noise. First, let us start with the expected value of this noise. That is simple. If I look at expected W, that is given as 1 over n summation over n expected W n expected C0n, which is equal to, remember, Wn the noise and the chip sequence, they are obviously independent because the noise is the noise processed at the receiver, the chip sequence is randomly generated at the transmitter, both of them are independent random processes. So, this is nothing but summation over n expected Wn expected C0 of n, and both these expectations, that is expected value of the noise and expected value of the chip, both are 0 because the noise is also 0 mean, the chipping sequence, the random spreading sequence also 0 mean, hence this is nothing but 0 over n, which is 0. So, the expected value is trivial, that is 0. That is also fairly straightforward to see that the expected value of the noise at the output is 0, because the expected value of the noise at the input is 0, the system is linear. So, the expected value of the noise at the output is also 0. That is another way to see it. But more importantly, what is the power? If I were to look at what is expected, what is the noise power, that is, if I were to ask what is expected W square, what is that value? Let us look at that. For that we have to look at expected, I will write W square as summation over m 1 over n summation over m W m C 0 of m, this whole thing product with 1 over n summation over n W of n C 0 of n. I can combine these two summations as W square equals 1 over n square summation m summation n W of m times W of n times C 0 of m times C 0 of n. Now, when I take the expected value of W square, if I take the expected value both on the left and the right, I will move the expected value expectation operator directly inside the summation, that is expected W m W n C 0 m C 0 n. Now, similar to the cross correlation between the spreading sequences, we can see that this W m W n C 0 m C 0 n are all independent if m is not equal to n. So, if m is not equal to n, this splits into 4 expectations: expected W 0 m into expected W n, expected C 0 m into expected C 0 of n, all of which are 0. Hence, this is 0 if m is not equal to n. If m is equal to n, that is the only term which survives, that is n square. I am assuming now m equals n. This now splits into expected C 0 square of m. Remember, m is equal to n. So, C 0 m into C 0 n is nothing but C 0 square of m. Similarly, W m into W n is nothing but W square of m. Hence, and W and C 0 are independent. Hence, this splits into 2 independent expectations: expected C 0 square m into expected W square of m. Now, expected C 0 square of m, C 0 square of m, C 0 of m is either plus or minus 1. So, in both cases this is expected, this is 1. Expected W square of m has an interesting interpretation. This is nothing but the power in the noise, because expected W square of m, it is the average value of W square, which is nothing but the average value of the square of the amplitude of the noise, which is nothing but the power of the noise. Hence, this is sigma W square. Alright, the noise is W, hence this is sigma W square. Hence, this expectation reduces to expected value of W square equals 1 over n square summation over n sigma W square. This is nothing but n sigma W square divided by n square. This is nothing but sigma W square divided by n. This is the noise power at output of this is the noise power at the output of the decorrelator. So, we have two components. So, we have looked at this thing, we have looked at the multi-user interference component. We said that the multi-user interference component is P1 over N, and we have looked at the noise component. We have said the noise component has variance sigma w square over N. Look at this interesting thing, that similar to multi-user interference, even the noise at the output, the noise variance is sigma w square at the input. However, at the output, when you despread or decorrelate with the spreading sequence, the noise power also reduces by a factor of 1 over N, and as N tends to infinity, that is, if you have large codes, the noise power at the output tends to 0. Hence, this is an interesting factor which is decorrelating with the spreading sequence suppresses the interferer, and it also suppresses the noise by a factor of N. Hence, it results in a gain of N in SNR. That is the reason it is known as the spreading gain. Hence, the SNR at the output, let us now write the expression for the SNR. The SNR at the output, remember the output is nothing but A0, which is the desired signal in the presence of the interferer, which is P1, which has power P1 over N, and the noise which has power sigma w square over N. Hence, the SNR is nothing but expected, that is the power in the desired signal, which is expected A0 square divided by the power in the interferer plus the power in the noise, which is sigma w square over N. Expected A0 square is nothing but the power in the signal of user 0, that is nothing but P0. So, that is nothing but P0 divided by P1 over N plus sigma w square over N. As we said earlier, this is the multi-user interference, that is the MUI component, and this is the noise component. And look at this, both of them are suppressed by a factor of N. Hence, the net SNR is equal to, at the output of the receiver, is equal to P0 divided by P1 plus sigma w square into N. This is the expression for the SNR, and most important point to note here is that you have a factor of N, that is your SNR, there is a factor of, there is a gain of capital N, and as the spreading length N increases, your gain, SNR gain, is increasing. This is known as the spreading gain of the system, because it arises from the spreading code, and this also has another technical name in CDMA. This is known as the processing gain. In a CDMA system, there is a gain of capital N, which is the length of the spreading sequence. This is known as either the spreading gain or the processing gain of the CDMA system. Hence, you can transmit at a very low transmit power, because at the output of the receiver you have a gain of capital N. That is why in the CDMA systems typically you have very low transmit power. So, the idea is essentially you are transmitting over a wide bandwidth. Remember, CDMA is a spread spectrum system, except you are transmitting at a very low power. So, using a wide bandwidth and very low power. All right. So, that is the essential SNR of a CDMA system, and so let us look at the advantages of this code division for multiple access system. Let us look at the advantages. What are the advantages? So far we have looked at CDMA, that is code division for multiple access, but what are the advantages of this CDMA system over other traditional systems like TDMA or FDMA based on time division or based on frequency division for multiple access? First, the first advantage of this CDMA system, the first advantage is what is known as jammer margin. The first advantage is what is known as jammer margin or protection against jammers or protection against jammers. Now, what is a jammer? Let me describe this schematically. Let us say I am trying to transmit to a base station. Let us say a desired user is trying to transmit to a mobile station. There might be another disruptive user. Let me draw this with a different shade. There is another disruptive user who is transmitting with a very high power in the same base station to disrupt the communication of this desired user. So, this user is the desired user. However, there is another malicious or there is a disruptive user. This is a disruptive user who is transmitting with a very high power so as to cause interference and block the communication. So, what is a jammer? This is a jammer essentially. So, who is a jammer? A jammer is essentially a disruptive user. A jammer is a disruptive user who transmits with very high power so as to disrupt communication. The key word here is disrupt. That is, a jammer is essentially disruptive or a malicious user who transmits with a very high power so as to cause interference, that is to cause heavy interference to your signal so as to block your communication or stall your communication. Now, so jammers are a significant problem, especially in secure communication. So, jammers are a significant problem. So, jammers are a significant problem, especially in secure So, jammers are a significant problem in especially secure communication, especially when you have high security communication links. For instance, if you have military communication links where information needs to be transmitted very securely, jammers can cause a significant problem by disrupting the communication link. And in fact, one of the earliest uses of CDMA therefore was during the times of World War II, so that you could provide a secure communication link for the army so that it is resilient to jammers. Now, how is this done? The idea is very simple. So, CDMA can provide jammer suppression or provide a margin against jammer, and the idea is very simple. As we have seen here, if the interferer transmits with the power P1, his interference is suppressed by a factor of n. So, you can employ a very large spreading code to suitably suppress the power of the interferer, and the same logic can use to suppress the power of a jammer. So, let us say a jammer is transmitting with a power Pj. So, let us say jammer is transmitting with power Pj, then the SNR, the interference, look at the interference power at receiver is Pj over n. So, by using CDMA, I am able to suppressing the jammer power of the jammer by a factor of n. In fact, you can employ very large spreading sequences of length 1024, 48 and so on and so forth, or even in the tens of thousands, so that this Pj over n is suppressed by 20 dB, 30 dB, 40 dB, so on and so forth. So, I can employ a suitably long spreading sequence to suppress the jammer power below a desired level. So, this results in, so employing a long spreading sequence results in jammer suppression, results in jammer suppression. Hence, my CDMA, my power at SNR at the output is nothing but, as we have seen earlier, the SNR is P0 divided by Pj over n plus sigma square W square over n. Hence, by employing a long spreading code, I am able to suppress the power of the jammer. Now, because I am suppressing the power of the jammer, this will not cause significant problem, because now the power of the jammer is reduced by a factor of n. So, this provides jammer suppression. This provides jammer suppression and this is also known as a jammer margin. A jammer margin is nothing but, now you have a more margin in terms of transmit power, because the jammer power is being suppressed by a factor of n. If you did not have this margin, then you have to transmit at a very high power so as to overcome the interference caused by the jammer. Now, the jammer power is being suppressed by decorrelating with the code, because remember, now each user is transmitting along a code. As long as the jammer is unaware of this code and these codes are protected very securely, then the jammer power is suppressed at the output, which means now we have more margin in terms of the transmit power. Hence, CDMA is a very key technology in secure communications, because it suppresses the malicious users who are known as jammers. Alright, so let us come to the second advantage of a CDMA system. This advantage is slightly technical, so we will have to go over it in some detail. So, let us come to the second advantage of CDMA system. The second advantage of a CDMA system, so let me write second advantage of CDMA is what is known as graceful degradation. The second advantage of CDMA is also known as graceful degradation. Now, what is graceful degradation? For this, we have to build up slight amount of theory. We have seen that the SNR in the presence of two users, SNR is nothing but P0 divided by P1 over n plus sigma W square over n. This is when I am multiplexing the signals of two users, that is the desired user is P0 and the interfering user is P1 is 1. I can also have multiple users, that is I can have interference, that is I can have not only one interferer, but I can have k interference. So, I can have k, in general there are k interferers. In general there are capital K interferers with powers P1, P2 up to Pk. Now, in the presence of K interference, I can simply modify this expression. There will be a factor of Pi over n for each of the K users. Hence, the general expression for SNR in the presence of K interference, hence SNR, where this is the SNR in the presence of K interferers SNR in the presence of k interference is nothing but P 0 divided by the power of each interferer reduced by a factor of So, these are the k interfering users, these are the k interfering users. The power of each interfering user is suppressed by a factor of n. The power of each interferer is suppressed or attenuated by n. Is suppressed by a factor. The power of each interfering user is suppressed by a factor of n. Hence, I can write this succinctly as SNR in the presence of k interfering users is nothing but SNR equals P 0 divided by summation of I equals 1 to capital K P I over n plus sigma W square over n. This is the power SNR in the presence of. So, this is the SNR in the presence of with K or capital K interfering users. Now, let us say there is a new interferer, there is a k plus 1th interferer who is added to the system. Consider addition of k plus 1th interferer. What happens when you add a k plus 1th interferer? That interferer will interfere with reside user 0, however, his power will also be suppressed by a factor of n. Hence, the new SNR or the new SNR, this is after addition of k plus 1th user is nothing but P 0 divided by summation I P I over n, I equals 1 to k. There is also a k plus 1th user whose power also adds as interference power P k plus 1 over n plus sigma W square over n. So, the newly added user, that is the k plus 1th user, causes an interference of only P k plus 1 over n at user 0. Now, this user k plus 1 will also cause an interference of P k plus 1 over n at user 1. He will cause an interference of P k plus 1 over n at user 2. So on and so forth, he will cause an interference of P k plus 1 over n at user k. So, at the general ith user, I naught equals k plus 1, that is at any ith user I naught equals k plus 1, interference caused by k plus 1th user is P k plus 1 over n. Hence, the interference caused at any ith user I equals 0, 1 up to capital K I naught equals, that is I naught equals k plus 1, the interference caused at each user is power P k plus 1 over n. Hence, his interference power is being equally absorbed by all the users in the system. That is, he is not causing more interference at one user and less interference at another user, rather his interference power is being equally divided amongst all existing users. This leads to what is known as graceful degradation, because the interference power is absorbed by each user equally. The performance of each user decreases a little bit symmetrically, rather causing too much interference at one user and bringing the power of that user down completely and leaving the other users unaffected. This is affecting each user by a small amount, because this is distributing the interference, hence this leads to graceful degradation compared to other existing systems before, and this is a very important property. So, because of the time I have to end this lecture at this point. We will start the next lecture again at this point and complete this point and look at other advantages of CDMA. Thank you very much.